We now continue with the section 8.1 notes. We're currently in example 4 on the third page, and we're ready to do part B. And we're dealing here with systems of equations that are either inconsistent or dependent. So our previous example was that of an inconsistent system where we obtained a contradiction when we used the substitution method. In the second example, part B of example 4, the system is set up best for elimination or addition, whatever you want to call it, because of the fact that the x's and the y's are lined up on the left-hand side of the equation, and it'd be rather easy to eliminate either x or y. If we think about, let's say, eliminating y, we could multiply the bottom equation by 3 so that we have opposites for the y terms. 9x minus 3y equals 15. We would just recopy the first equation, multiply every term of the second equation by 3, minus 9x plus 3y equals negative 15. So now notice that in attempting to cancel the y terms, I also end up canceling the x terms. Not only that, I cancel the terms on the right-hand side as well. Everything's opposite. So when you add the equations, the left-hand sides add to give you 0. The right-hand sides add to give you 0. That is, you get 0 equals 0. This is called an identity. If you're using the elimination or addition method to solve a system and it turns out to be a dependent system, you'll always get 0 equals 0. If you're using the substitution method, you can get other types of identities, such as 2 equals 2 or something like that. But if you obtain an identity such that the variables completely cancel out, then you would conclude that you are dealing with a dependent system. A dependent system has an infinite number of solutions. And by dependent, we're saying really that the two equations algebraically are equivalent. That's why they just completely cancel each other out. To represent the infinite solution set of a dependent system, we can take one of the equations, it doesn't matter which one you work with, let's use the simpler one, the second equation, and solve it for either x or y. It's easiest here to solve for y. So let's write the second equation as y equals 3x minus 5. And if we then let our y-coordinate be represented by 3x minus 5, and our x-coordinate be represented by x, our solutions have the form x comma y equals x comma 3x, x comma 3x minus 5. I hope there it goes, my pen is working now. Now, you might wonder what this represents. This is basically a way of representing all of the points on the graph of y equals 3x minus 5. You have to understand that the graph of y equals 3x minus 5, that is, the graph of negative 3x plus 5 equals negative 3x plus y equals negative 5, the second equation, is identical to the graph of the first equation. The two equations have the same graph. So what we're doing is describing the set of points on that line in terms of one variable. And then you could substitute different values in for x and obtain different solutions, really an infinite number of solutions of the system. For example, if you substitute in x equals 1, just a second. If you substitute in x equals 1, for example, you would obtain the ordered pair 1, and then 3 minus 5 would be negative 2. Well, 1, negative 2 is one of the solutions of the system of equations. It satisfies both equations in the system because the two equations are algebraically equivalent. So this is just this x 3x minus 5 is just a general way of describing the set of points on the line that represents either of these equations, and just gives us a convenient way of representing the form of the solutions of the system. It's sometimes referred to as the general solution of the system, since it's expressed in terms of a single variable. We now turn to a couple of applications of systems of equations. There are many situations where systems of equations arise. One of those situations from economics is supply and demand situations. Usually you have a supply equation and a demand equation. If those equations are linear, then to solve a supply-demand problem, you have to solve a linear system of equations. As the price of a product increases, demand for it decreases, and the supply increases. So you can have an equation that relates price to the amount supplied and price to the amount demanded, two separate equations. And then given the supply and demand equations relating price P to the quantity X of a product, we seek to obtain what's called an equilibrium point. That is going to be in an ordered pair of the form X comma P. Here P is playing the role of Y, that satisfies both equations. When both equations are satisfied, then you have obtained a price that makes supply equal to demand, and that puts your market in equilibrium, so that you have neither a you don't have any surpluses, you don't have any losses. That's not the right word for it, but I can't remember the correct term. All right, so full disclosure, I paused the video for a moment and looked it up. The word I wanted was shortage. Shortage. I almost forgot it again. You either have if you don't have equilibrium, you have a surplus, or you have a shortage. I used the word loss instead, since I was at a loss for the proper word. In any event, let me move on. We want to find the equilibrium point. That's going to be the solution of the system of equations, where the price for supply is equal to the price for amount demanded. So in this particular case, if you look at our two equations, both of them are solved for P. So here it would make sense to use substitution. If we simply substitute the right-hand side of the first equation into the left-hand side of the second equation, then it's basically like setting the two right-hand sides equal to each other. So we're replacing P in the second equation with 20 plus 0.002x. That's basically like just setting the left-hand side equal to the right-hand side. I'm sorry, what I meant to say is setting the right-hand sides of both equations equal to each other. Forgive me. All right, so we set the right-hand sides equal to each other. Since both of them equal P, we've essentially accomplished a substitution. We've eliminated P. Now we can solve for X. Okay, to solve for X, what we might do is add 0.008x to both sides, and then simultaneously let's subtract 20 from both sides. And what that's going to give us on the left-hand side is 0.01x, and on the right-hand side we're going to obtain 57. And if we divide both sides by 0.01, 57 divided by 0.01 is going to give us 5,700. So that would be our x, and then once we have our x, we can solve for p using either of the two equations, either the supply or the demand equation. So if I use, say, the supply equation, p is equal to 20 plus 0.002 times 5,700. That's our x. And that would give us 20 plus, so we have 0.002 times 5,700 is 11.4 or 11.40, since I can do dollars and cents. And that would give us 31.40. So that's suggesting that when the amount supplied and demanded is set at 5,700 units, then we would be using a price of $31.40. I guess a better way to say it would be if the price were set at $31.40, then the amount supplied and the amount demanded would be in equilibrium, and that equilibrium quantity would be 5,700 units of whatever it is that you're whatever commodity you happen to be dealing with in this situation. Okay, so your equilibrium point would be 5,700 for x and 3140 for p. So we won't have enough time to do the final example, so I'll just put that on the next video. That concludes this video.